Okay. Okay, so at the end of lecture today, I started talking about the quantum numbers, and that's where I'm going to be picking up with is the quantum numbers. I only introduced the various quantum numbers, but we're going to go into a little bit more detail about them. And then somewhere shortly after that, we'll probably wind up taking a break, coming back, and then discussing electron configurations and how it's all interrelated. So just as a reminder related to our discussion today, what are you doing to me? I introduced the first quantum number, which is the principal quantum number. Which is represented with a lowercase n. And basically, again, this describes how far away from the nucleus an electron resides. It is also referred to as the shell for that electron. The principal quantum number really is an important number, relatively speaking, because it in describing how far away from the nucleus the electron resides, it also is describing how much energy is going to be necessary to remove an electron to make a cation, or how much energy is going to be given off when an anion is made. So it is a very important quantity that we will wind up using. Now, as far as the principal quantum number, it can be any whole number. So it can be equal 1, 2, 3, and so on and so forth. Basically, 1 means that the electron is right up against the nucleus. And the higher the number, the further away from the nucleus the electron resides. The second quantum number is going to be the angular momentum quantum number. And the angular momentum quantum number is represented by the letter L. The angular momentum quantum number describes the electron density shape where the electron is most likely found. This is also described as the subshell. The rule for this one is that it can be any number between 0 and n-1. Now, the subshell is extremely important because, again, it describes the shape of the of this. It describes the shape where you're most likely to find the electron. Now, we do have very specific ones. So if L is equal to 0, we consider that to be an S subshell. And it is going to be spherical in shape. If L is equal to 1, it is going to be a P subshell. And it is going to be dumbbell in shape. If L is equal to 2, then we're talking about a D subshell. And we're talking about 4 of the 5 are cloverleaf in shape. And then I don't have a perfect word to describe L equals 3 other than it is our F subshell. These correlations between the L number and the type of subshell are going to be extremely important when we start trying to figure out the when we start talking about orbitals and when we start talking about the electron configurations. Then you have the magnetic quantum number. And the magnetic quantum number describes where in an XYZ coordinate plane the electron is likely to reside. As far as this number is concerned, it is the specific orbital. And our M sub L, oh, and I should say that it's M sub L. And M sub L can be any value. Is going on. Between a negative L and a plus L on a number line. For a set of quantum numbers to be valid, the quantum numbers have to follow the rules. And what I mean by that is, again, N has to be a whole number. L has to be between 0 and N minus 1. And M sub L has to be between negative L and a plus L. If it doesn't follow the rules, then it's not valid. So what we're going to do first is we're going to build these quantum numbers. And I realize right now this concept of quantum numbers is completely vague. I mean, after all, it may, in a sense, stay vague because this is based off, basically what we're deriving here is based off of a mathematical calculation that is predicting the most likely location to find an electron. But as we progress, my goal is for it to become less vague as we narrow in and we actually get into the electron configurations. But for now, we're going to continue just working with the rules. So it may seem a little vague at this point, but hopefully as we move it through today, it will get better. So let's just begin with our first N value. Remember, N has to be anything, it has to be a whole number. That's its rule. And we start with 1. From there, we move to the L value, which is the angular momentum quantum number, which can be anything from 0 to N minus 1. Well, let's think about this from a mathematical standpoint. That means we are talking about something that can be 0 to 1 minus 1, because that's what our N is. Or in other words, it has to be equal to 0. So our only option for an L value in this particular, the only subshell that can exist in shell 1 is an L equal to 0, which happens to be an S subshell. Then we move on to M sub L. M sub L can be anything from a negative L to a plus L. Well, if we think about this mathematically, that means it can be negative 0 to plus 0, or in other words, our only option is 0. So in the first shell, you have an S subshell, and there is only one of those. So if we were to explain what's going on, we would say in the first shell, the only subshell that can exist is an S subshell. And there is only one orbital in the S subshell. Questions so far? No, the orbital is how many values, numerical values, are there for M sub L. So yeah, this is your orbital. This is your subshell. And this is your shell. Since there's only one value available in the M sub L, only one M sub L value available, there's only one orbital available. Okay. So to see this in more light, let's go to principal quantum number 2. For principal quantum number 2, L can be anything from 0 to n minus 1. So it can be anything from 0 to 2 minus 1. Or in other words, we have the option of 0 and we have the option of 1. Those are our options. Now we have to take each of these L values separately to do the next thing, because the next piece is talking about the M sub L. So for our L of 0, that means our M sub L can be a -0 to a +0. Well, that means it's still 0. Now for our other one though, which is our P subshell, now that one, we have a choice of M sub L is anything from a -L, -1, to a positive L, a +1. So in other words, that can be a -1, a 0, or a 1. Because it's whatever values are on the number line. So we have the choice of a -1, a 0, or a 1. So let's just describe what that means. So in the second shell, from the nucleus, there are 2 subshells. An S subshell and a P subshell. The S subshell has only one orbital. The P subshell has 3 orbitals. Questions about those statements? Oh, let me roll it up so you can see those statements. I'm letting people catch up with me writing. I know it's easier when you're doing the writing than to read and write. At this time, we only have elements in the first 7 shells. But that doesn't mean that we can't have an 8th shell or a 9th shell or a 262 shell. We just haven't gone that far yet. Right now, we've only found them up through the 7th shell, but we could continue. And as long as the rules are valid, even if it's the 262 shell, as long as the rules are valid, it's a valid set of quantum numbers, whether we found anything yet or not. Now, there is one more quantum number. Today and on Tuesday, our world revolved around that of hydrogen. Hydrogen just had that one proton and that one electron. It was easy. But when you start getting a multitude of electrons, you have to have another quantum number. A 4th quantum number is required because 2 electrons can exist in each orbital but they cannot have the same quantum numbers. So we have a 4th quantum number, and that quantum number is called the spin quantum number. Which is represented with an M sub S. There are only 2 possible values. And those are a +1/2 or a -1/2. And what those values represent is they represent the spin. So if we were to take an element and we were to shoot a ray of that element in between a magnet, we would see some electrons go this way and some electrons go that way. And it is this idea of the electrons being able to flow in different directions that causes us to say there are 2 spins, a +1/2 and a -1/2. So if we're going back up here, to my original, and I add an M sub S of a +1/2 or -1/2, which is my spin quantum number. Then for each of these orbitals, because each orbital can have 2 electrons, in each orbital, you'll have a +1/2 and a -1/2. For the 2s, you'll have a +1/2 and a -1/2. For each of the 2p's, you'll have a +1/2 or a -1/2. Now, right off the bat, hopefully what you will realize is that if I have an S subshell, the maximum number of electrons I ever get are 2 in an S subshell. If I get a P subshell, I can have 6. That actually is going to help us when we get into the periodic table. Which is where we're headed next. Folks, you don't have to memorize. I mean, yeah, I know the rules, but I can also look at the periodic table and tell you the rules. All of these are embedded in that periodic table. How? Well, so one way that they're embedded in the periodic table is that the period number is related to the principal quantum number. It's not always the same thing, but there is a relationship. Number 2, the periodic table is divided into blocks based on the angular momentum quantum number. Number 3, the number of electrons that can exist in each subshell is related to the block. On the periodic table. So now I'm going to try to draw the periodic table. What the heck did this do? Okay. So 1, 2, 3, 4, 5, 6, 7. Okay. Let me. You can see. Oh no, you can't see it. Okay, I don't know which part to get rid of. Okay, so this is your periodic table, me and my coloring, but I think it's useful to see it in color. So N is our principal quantum number. Well, I'm gonna let everybody catch up. Actually, this is a good spot for a break, even though we've only been at it for about 30 minutes. That way everybody can catch up. So we're gonna take like a 12-minute break. And that way, when we come back, we'll start into this and electron configurations. That way, everybody that needs to color can color, but also you can. There is, I don't know if y'all are aware, there is a Coke machine and a vending machine right through the door that direction. Or you do have enough time to maybe run and get something else if that's your desire. And the bathrooms are that way. Or they know. Everybody's by the. Thank you.
Someone in the group me asked for the Zoom link.
Trying to figure out the best way to do this. Groupie.
help.
As
He's doing well. I just feel like this week's been crazy.
well, I'm sure.
Hopefully next week we'll be back to normal and she'll be back to class. She's wrong. Nothing so far. Relative. Some of the numbers are always crazy though. Well, most people do, and it's always that way.
When you say subshell, is it like another circle? Or like, what are we?
No, so, described as a, so you've got your shell,
It's like all that.
subshells are within those shells. It's the word sub. So some of them are circles inside the shell. Some of them look like dumbbells inside the shell. Some of them look like clover leaves inside the shell. I will show you at the very end how I can put them all together.
That's what I'm struggling with, just putting everything together.
We're gonna go into electron configurations, then when I'm done with the electron configurations, then I'm going to actually try to draw
That's great.
everything so that you can see how it kind of meshes together to make the atom.
Yes, ma'am.
I am not the most artistic person in the world. And when the art really tries to be better, I usually just go find pictures and have them preloaded. Because I'm that bad.
So I'm not throwing this. More minutes. Think we're back. So I'm gonna jump back in. Okay, so given time to actually draw it, this is how the quantum numbers are directly related to the periodic table, and also how you're going to build the electron configuration given the periodic table. So on the left-hand side of the periodic table, you have your period number. And I am just assigning that period number the value of X. So just as a variable. Then the group 1 and group 2 are known as the S block, because the elements in that portion of the periodic table, their last electrons wind up in the S subshell. And it's specifically, I call it the NS block. So in other words, N is your principal quantum number. It is equal to the period number in that case. So for instance, hydrogen, which is the first element on the periodic table, its last electron will be in the 1s block. And I actually made a tiny, tiny mistake. Because helium's a little bit odd. That's my tiny mistake, is helium's an oddball. For instance, lithium though. Let's go to lithium, which is element number 3. It is on this in the second period. The second period, but it's still in that S block. So it means that its last electron will be in the 2 second shell, S subshell. Now, on the right-hand side of the periodic table, you'll find the NP block. The principal quantum number, again, N being equal to the period number. So for example, carbon, which is element number 6 on the periodic table, its last electron is going to be in that 2, because it's in period 2, P subshell. All of the transition metals fall in the ND. So they're in a D subshell, which is cloverleaf in shape. But unlike the S and the P, when you get to the D, to figure out its principal quantum number, you have to take the period number and subtract 1 from it. So for example, scandium element number 21, which is the first element of the transition metals, while it is in period 4, it is in the 3, its last electron will wind up in 3D. And then you have your lanthanides and actinides. They are in the NF block. But again, N is not the period number. You have to subtract 2 from the period number to get to that principal quantum number. So for example, cerium element number 58 on that periodic table, it follows after lanthanum element 57. Lanthanum is in the 6th period, but to figure out where the last electron for cerium is going to be, we're going to take that 6, we're going to subtract 2, and we're going to get 4. So cerium is actually in the 4s. So if you wanted to look at it from a slightly different perspective, you could go in and say, okay, well, hydrogen and helium are 1s. Then you have your 2s followed by your 2p's, your 3s followed by the 3p's, your 4s followed by the 3d, followed by the 4p, your 5s followed by the 4d, followed by the 5p, your 6s actually is followed by the 4f's, then the 5ds, then the 6p's, and then the 7s goes 5f, 6d, 7p. So that's another way you can write it if that's better for you. But my entire point was the majority of your, if you look back to the statements I made before this, the principal quantum number is related to the period number. I just showed you how it is related to the period number. The periodic table is divided into blocks based on the angular momentum quantum number. We just talked about the angular momentum quantum number. While we didn't describe it by a number, an S is always 0, a P is always 1, a D is always 2. That is something I described previously. And then the number of electrons that can exist in each subshell is related to the block on the periodic table. So how many elements are across the S block? If you were to take period 2 and walk across it, how many elements are in the S block? Hence, 2. If you were to take the second period and go over to boron through neon, how many are in the P block? 6. The quantum numbers are there, folks. Guess how many electrons you can add to the D block or to D subshell? 10. And by the way, these things are basically addresses. My husband and I live in our home, which has an address. The address is in Plummerville, which is the city, which is in Arkansas. So it's, all we're doing is we're talking about an address for an electron instead. But it's just like an address. That's all it is. That's all quantum numbers are addresses. So. Okay, so we're going to start building electron configurations. An electron configuration describes where each and every electron in an atom resides. Electron configurations are extremely useful. They give us a lot of information. For one thing, they can tell us whether we're in a neutral state or in an excited state. How do we know if we're in a neutral or an excited state? A neutral state means that the electrons enter the atom as expected. Neutral means that the electrons enter the atom as expected. Whereas excited means that they're not in the order expected. We can describe the size of the atom. Now, there's a couple of things that are going to go into this. One of the things that will go into this is going to be the principal quantum number. Which causes shielding. But another thing that is going to go into this is going to be the effective pull of the nucleus on the outer electrons. Another thing this directly impacts is the amount of energy needed to make ions. All of these things are related to the electron configuration. And the electron configurations are related to quantum numbers. So it's an entire story that we're telling here. Now there are three types of electron configurations we're going to work with. We're going to deal with the complete electron configuration. Which describes every electron. We're also going to deal with the noble gas configuration. Which is a form of shorthand notation. And then we're going to deal with the box diagram. And actually, the box diagram is going to be useful for determining the quantum numbers. Okay. So we're going to start out with the simplest of all elements, that element being hydrogen. I plan to do hydrogen, helium, boron, and nitrogen today, and then I'll pick up with a couple more on Tuesday. Okay, so hydrogen, its atomic number is 1. So it has 1 proton and it has 1 electron. So we need to describe where that 1 electron resides. And unfortunately, I'm stuck scrolling up and down, and you get the drift. Here is hydrogen. Hydrogen is in the NS, where N is equal to the period number. So it is in the 1s because that was the period number. And hydrogen is the first element in that period, or first element in that block. So there's only 1 of them. This would be the complete electron configuration for hydrogen. Now, unfortunately, I cannot do a noble gas configuration until we get to lithium at the earliest. Because you've got to be past a noble gas to write a noble gas configuration. But we can go ahead and do a box diagram. Now, and I'm going to scroll way back up to this thing. How many orbitals were in the 1s? In other words, how many numerical values are in the 1s? Orbitals. You have it, 1. So down here, when we do the box diagram, we're going to draw 1 line. and we're gonna label it as our 1s. Now, people, books and maybe even active, I can't remember. We'll show it as boxes. I do it as lines because otherwise it takes a long time to draw a gazillion boxes later on.
Can you show us just for hydrogen what it would look like for active, just so we know?
I can't remember if it's a line or a box. I mean, it'll either look like this or it'll look like this, and I just can't remember which.
I didn't know if there was gonna be some like other lines in the box.
No, it's either a box or a line. And then we do have to add the electron. We said that there was one electron. Now, it is convention to put the one electron in spin up first. And that is what we do. So when we start doing these, we will put an up arrow, that is a +1/2. Or we'll put a down arrow, which is a -1/2. Now, these you may see also as half arrows, and I know I'm notorious for it in the homework. So just keep in mind, you may see it as a half arrow or a full arrow. I've seen it both ways. So I'm showing it to you both ways.
Which one do you want?
I don't care which one. Both of them work for me personally. A lot of times I do the half arrow because it's faster, but you know, I've seen it both ways too. Folks, this is the box diagram right there. That's all there is to hydrogen's box diagram. Now let's get when we write our quantum numbers for anything, we always do so in this order. So you always list the principal quantum number. Then, in other words, we always go from furthest out and narrow it down and narrow it down and narrow it down. So we always start with the principal and go from there. Those things are embedded in this. So the numerical value here, folks, that is your principal quantum number. So that is a 1. The letter tells you what your L is, because remember, an L equal to 0 is an S, an L equal to 1 is a P, an L equal to 2. My thing just froze. An L equal to 2 is a D, and an L equal to 3 is an F. So since this is an S, that means our L is equal to 0. I'm going to skip IMSABEL briefly and go to the IMSABES because it's more obvious. IMSABES is described by the arrow. Again, this is a +1/2. So that's why it's an up arrow. Finally, your L. I mean, your IMSABEL. Trying to make sure I find a color that's obvious. The line is basically representing your IMSABEL. But unfortunately, you still have to be prepared to do the calculation. And so you've got to remember, IMSABEL is anything from a -L to a +L. In our case, that would be a -0 to a +0, or in other words, it is 0. And that is the quantum numbers for hydrogen's 1 electron. Let's go with helium. Helium is atomic number 2. It has 2 protons and 2 electrons. On our periodic table, helium is sitting over here. It is in the S block, hence the reason it's colored in, where N is equal to the period number. So it's in the 1s. But if you count over in that 1s, helium is the second element. So it's 1s2. You still cannot write a noble gas configuration, not until you get to lithium. So let's do the box diagram. Again, if we're dealing with an S subshell, we're only going to have one orbital. And in this case, you have 2 electrons, one up and one down. If you look at, other than whether it's double-headed or single, if you look at the previous hydrogen, you will see that the first electron pretty much looks identical. Well, it's also going to have the exact same 4 quantum numbers in helium as that was found in hydrogen for the exact same reasons. But let's talk about the second electron. Again, N is decided by the numerical value. Your L is related to the letter. Your M sub L is associated with the dash, which also comes back, it's still 0. But here's where no 2 electrons can have the exact same 4 quantum numbers. Because we are dealing with a spin down for our second electron, so it's a -1/2. Oh, my foot just went to sleep. Questions? Let's look at boron. Boron is element number 5. 5 protons, 5 electrons. On this periodic table up here, boron exists right here. Just like when you read a book in the United States, you start at the top left and you read from left to right and then go down the page. When we develop electron configurations, we start at the top left of the periodic table. We read left to right and go down the page. So we still have to start with the 1s. And we go through helium, so that's 1s2. That takes care of the top line, so then we move to the next line. And the first thing we have come across in the second row, or the second period, is the S block. And we have to go through that S block, and we're still not to boron. So it's 2s2. Then we move all the way over to the right-hand side of the periodic table. And when we get to the right-hand side of the periodic table, we are in the NP block, where N is equal to the period number. So we are in the 2p's. And boron just happens to be the first element in the 2p's. Now, I haven't been able to until now to do a noble gas configuration. If you notice, boron has everything that helium has. They both have a 1s2. So we can say that. We can say, hey, boron has everything helium has. And we say that by putting helium symbol in brackets. And yes, you do need the brackets. But basically that symbol within the brackets is saying that you have everything that helium has. Now it's only necessary to list what helium doesn't have, that boron does have, which is the 2s2 and the 2p1. That is the noble gas configuration for boron. Folks, when we talk about, so if we talk about sulfur, and we want the noble gas configuration, we start out by going back to the noble gas before sulfur, which is neon. And we put neon in brackets. By doing so, basically you can ignore everything on second period and up when coming up with the electron configuration. So it's going to be neon, and then we start here. 3s2, 3p4. Noble gas configurations get very handy when you get down to mercury, or even germanium, tin, all of those, because it cuts out a lot of writing. They're shorthand notation. Now, you can use, you will see me use both the complete or the noble gas configuration to figure out electrons. It all depends upon what I'm asking. Am I asking for the last ones I added to the structure, or am I asking for all of them? It all depends upon what I'm asking for. So with this, let's go ahead and write it all because it is a short one. So I'm going to use this one. Well, the 1s only has one orbital, and it has 2 electrons in it. S only has one orbital, and it has 2 electrons in it. How many orbitals were in the P though? 3. It goes 1, 3, 5, 7. SPDF. 1, 3, 5, 7. So odd numbers.
When you write it, like, you have to show, like, the, like, extra ones in order, right? You can- Is that right?
What now?
So, like, for, like, the P one, do you have to, like, since there's, like,
So
6 possible electrons?
I have to write all 3 orbitals, but when I fill it, I only put in the 1 electron. That is correct. Now, the S's, hopefully you got the quantum numbers. I want to do the 2p before my thing dies, and then I'll go to my pins when it does die, but. So 2, my N is 2. Then I got the L, M sub L, M sub S. The L, again, is decided by whatever the letter is. When the letter is P, L is equal to 1. M sub L is determined by our lines, but it's also determined by the equation that M sub L equals anything from a negative L to a plus L. Well, since our L, so this M sub L is equal to anything from a -1 to a +1. So it can be a -1, a 0, or a 1. And what I tend to do is I tend to go ahead and just write those in for the lines. So I would record this one as a -1. Because it's sitting on the -1 line. And then it is spin up, which is the last piece of the puzzle. So this is a +1/2. Those are the quantum numbers for that electron that was added to the 2p. Okay, before I introduce the very last one, which is going to be nitrogen, I do need to talk about degenerate orbitals. And basically what it boils down to is orbitals are considered degenerate when there is more than one orbital in a subshell. So P, so basically what it boils down to is P, D, and F all have degenerate orbitals. Now, the reason this is important is because you always place one electron in each degenerate orbital before pairing. And the reason we do this is because an unpaired electron is lower in energy than a pair, than when you pair them. Nitrogen is element number 7, so it has 7 protons and 7 electrons. You start at the very beginning. So we're going to start with the top left with the 1s, and we put in 2 of them because that's how many are in the 1s. Then we go to the 2s and we put in 2 because that's how many are in the s. And then we go over to the 2p, and the last 3 go into the 2p. What I want to show you, I'm not gonna worry about the noble gas configuration, but I want you to see the box diagram in specific. So an S only has one orbital, so that's one line, spin up, spin down. An S only has one orbital, so that's one line, spin up, spin down. A P has 3 orbitals, and so it is degenerate. Because it is degenerate, you place 1 electron in each orbital before pairing. So 1 would go in each of the 3 orbitals for the P subshell. Questions? We will do a few more Tuesday. But on Tuesday, I'll get into the anomalies and I will get into the, well, we'll get into the D subshell and then I'll do anomalies. And then we will move on from there and start getting into atomic size, ionization energies, and so on and so forth. That is it for today. I made it before my iPad died.
With the last thing you said, like I understand that it's degenerate. Can you explain that just like